So hello and welcome to lecture 5, which hopefully will be the last of the lectures on special relativity and electromagnetism. So we will start off today by looking at the transformations of the electromagnetic field tensor. And just to remind you of what this was, F mu nu, as we saw last time around, F mu nu was given by del mu a nu minus del nu a mu, and so let me just write this down for you. So we had F mu nu equals to del mu a nu minus del nu a mu. You could from there also define something which was F upper mu nu, which was given by the multiplication of two etas with this. So F was F upper mu nu, if you wish. If you wrote it in terms of matrix, was given by 0 Ex by C, Ey by C, Ez by C, all minuses here, and here it was Ex by C, Ey by C, Ez by C, 0 minus Bz By, Bz, 0 minus Bx, minus By, Bx, 0. So these were the entries. So this was the electromagnetic tensor, if you wish. This is something that will transform nicely under Lorentz transformations. So the transformations, so under Lorentz transformations, F prime F mu nu goes to F prime mu nu, which is given by lambda mu rho lambda nu sigma F rho sigma, or in matrix notation, this is F goes to F prime, which is equal to lambda F lambda transpose. So this was the form. So let us now look at explicitly what some Lorentz transformations will do. The first one we will not go into much detail is rotations. So remember that for rotations, your lambda is just given by 1, and there is this R matrix, which is a 3 cross 3 rotation matrix, such that R transpose R equal to 1. And if you do this, so the transformations of the electric and magnetic fields are as expected. So transformations formations of electric and magnetic fields are as expected. So what is expected? Electric fields just rotate, as do magnetic fields, and crucially, so here there is no mixing between E and B. Okay, so rotations, just deal with the spatial parts, does not involve the time direction, so you can just put this in and see. So what is going to happen is, if you take F, the the zero, so the matrices which either have either nu equal to the matrix elements which belong to the electric parts, either have to have mu equal to 0 or nu equal to 0, since this lambda, the 0 component of lambda is 1 and 0 components are all 0. So this means that the electric fields do not transform into magnetic fields, so they don't mix things up. Okay. Now, as you can well understand, the situation for the boosts will be different. So for boosts, so let's consider boosts along x-axis. So you would remember that for that, lambda is given by gamma minus beta gamma minus beta gamma gamma, and the rest of it is 1. So 1, 2 cross 2. So now what is going to happen is that you need to look at the transformation of the f's carefully. Okay, so let's do this. So what we saw there was that f prime mu nu was equal to lambda mu rho lambda nu sigma f rho sigma. So let's start with f01. Okay, so start with f01. f01, so which is, so f prime 01, let's keep a little bit of space here. Actually, let's move this here. F prime 01 is what? F prime 01 is, you need to put 0 instead of mu, rho stays, you need to put 1 instead of nu, sigma stays, f rho sigma, right? So now you need to sum over all rho and sigma. Okay, let's do this. So this essentially is lambda 0, rho 0, 1. I've not summed over sigma. Now let's keep this. F of 0 sigma. So this is where you take rho equal to 0. So now we are going to take rho equal to 1 and rho equal to 1. So remember that this essentially implies that there's a sum over rho and sigma which runs from 0 to 3, right? So this is what is implied. So let's just do this explicitly. So 0 1 lambda 1 sigma. So we are just doing the rho sum first. F 1 sigma plus lambda 0 2 f 1 sigma f 2 sigma plus lambda 0 3 lambda 1 sigma f 3 sigma. Now lambda 2 sigma and lambda 3 sigma are both equal to 0. So look at the form of lambda here. So there are no cross terms between 0. So 0 1 is there, but 0, 2 and 0, 3 are not there because this is a boost along the x-axis. No mixing of the t direction with the y direction or the z direction. So these guys, this and this would be equal to 0 because lambda 0, 2 is 0 and lambda 0, 3 is 0, okay? So these are not there. So what we are going to do is we are just going to erase this, okay? Oh, or yeah, let's just erase this. So, or maybe we can cut this out. Okay, so we are left with lambda 0, 0 and lambda 0, 1 here. And now we need to do the sum over sigma, okay? Again, so lambda 0, 0, lambda, let's look at, so you can have 1 and, you know, let's say sigma is 0, so this is f0, 0. Plus, now you want to put sigma equal to 1 out here. So lambda 1, 1, f0, 1 plus lambda 0, 1. Now again, if you want to put 1, 2 and 1, 3, lambda 1, 2 and lambda 1, 3 are both 0 because these are the cross terms which are not there. So we drop those two terms off. So the second one is going to be lambda, again lambda 1, 0. So now we put sigma equal to 0, f1, 0 plus lambda 0, 1, lambda 1, 1. So that's f1, 1. Now we need to keep in mind that f0, 0 is equal to 0 and f11 is equal to 0, right? So these terms will also go off, okay? So these terms are not there. So what you're left with is lambda 0, 0, lambda 1, 1, f0, 1 plus lambda 0, 1, lambda 1, 0, f1, 0. Very simple. You just have to just carefully sit down and put all the indices in. But once you do that, this is very simple. Okay. So this is, now we can put the values in. And you remember that this on the left hand side, this is E primed x over C. And on the right hand side, this is going to be, so gamma naught, so lambda naught naught, lambda 1, 1 are both gamma. So this is gamma squared. F0, 1 is Ex over C. Lambda 0, 1 and lambda 1, 0 are related by a sign. So that's so these are both minus beta gamma squared into f1, 0 is actually minus of f0, 1. So this is given by a minus sign. Sorry, this is going to be a minus, this is going to be a minus. So this is Ex over C. So what happens is that this is, so that means that Ex primed is equal to gamma squared. So let's make sure that we get this right. Gamma squared minus gamma squared beta squared into Ex. Now remember that gamma is 1 over, so this is, you know, gamma squared into 1 minus beta squared into Ex. Gamma is root over, so gamma squared is 1 minus v squared over c squared. Inverse, this is 1 minus beta squared inverse. So you have gamma squared into 1 minus beta squared. This stays the same. So this essentially means that Ex primed is equal to Ex. And at the end of the day, when all the dust settles, you get Ex primed equal to Ex, okay? So I did this very slowly. And so now the next one I'm going to be doing a little quicker, okay? So let's look at f primed 0, 2. And this is going to be lambda 0, 0 rho lambda 2 sigma f rho sigma. So the only things that, so let's just be reasonably careful with this. So lambda 0 rho, and the only thing that lambda 2 sigma is not non-zero for only lambda 2 2. That is identity. So this is rho 2, okay? So this means that now you need to sum over the rho now. So the only ones that are non-zero is gamma naught naught, this 2 2 f naught 2 plus gamma naught 1 lambda 2 2 f 1 2. So this is given by, so let's put the indices in. Let's put the values in. This is minus Ey primed by C. Gamma naught naught is just gamma. Lambda 2 2, lambda naught naught is just gamma. Lambda 2 2 is identity. F 0 2 is minus Ey over C. Lambda 0 1 is minus beta gamma. Lambda 2 2 is identity. And F 1 2 is B of Z. So this yields that Ey primed is given by gamma into Ey minus V into Bz, okay? So this is what we have for Ey. And we are going to do a third one, which is f primed 1 2. So this is lambda 1 rho lambda 2 sigma f rho sigma. So this is again lambda 1 rho lambda 2 2 f rho 2. This is, so you again have the 0 component which is non-zero, f0 2 plus, and the 1 component which is also non-zero. So this essentially means that minus Bz primed is equal to minus beta gamma into minus Ey by C minus gamma to Bz. So Bz primed is gamma Bz minus V over C squared Ey. Okay. Now similarly you can do the rest, and the final result of a boost along x-axis is the following. So let's just write this down. So we saw this, Ex primed is equal to Ex. We also saw the next one, which is Ey primed was gamma Ey minus V Bz, and Ez primed was gamma Ez plus V By. For the magnetic case, Bx primed stays the same again. By primed becomes gamma By plus V over C squared E of Z, and Bz primed becomes gamma Bz minus V over C squared Ey. So this is how the electric fields and magnetic fields change when there is a boost applied to it. It's very clear here with these explicit transformations that under boosts, electric fields change into magnetic fields. So in order to demonstrate this, now let us look at a boosted line charge. Okay, boosted line charge. Before I do this, let me first remind you of a few very basic things which you guys have done before. Okay, and there, that, and that, and so let's take an electric field. We want to look at the electric field. So this particular distance, let's call this R, the radius of R, we call the length L. So electric field of a uniform electric field due to a line with uniform charge This is something that you have learned a long time back, and you have used Gauss's law to do this. So integral E dot ds, as you remember very well, in this particular case is going to be eta L by epsilon naught, where eta is the line charge. So that's the total charge enclosed by the surface. This is just E of r to 2 pi r into L is eta L over epsilon naught. So this essentially means that the electric field E of r, which is in the direction r cap, is eta over 2 pi epsilon naught r to r cap. And the second thing that I want to remind you is, let's look at another cylinder. Let's draw another cylinder, and this is a wire, and I want to draw an Amperian loop around the wire. Okay, and there is an current I which is in the wire, and this is Z, this is radial direction, and this particular direction is also theta. So theta is this way. So the magnetic field due to a uniform current in a wire is just given by Ampere's law. So you the closed loop of this B dot dr is just B for 0 to 2 pi r d phi, which is nothing but 2 pi r b of r. This is equal to mu naught into I. So using Ampere's law, you get B as mu naught I by 2 pi r, and the direction is phi cap. Okay. So this was very well known things from long ago. Now what we suppose let's suppose we have a line of uniform charge density lying along the x-axis. Line of uniform charge density along x-axis. So along x-axis, so E is going to be simply eta. The distance r is going to be just y squared plus z squared. So this is r cap, so we can just look at this as so this is the electric field, and the magnetic field here is 0, right? So B is equal to 0. Now we want to look at this from the perspective of an observer who's moving with the speed v in the direction x, which is parallel to the wire, in frame S prime, which moves along x-axis at speed v. So now there is going to be a change. Now what did we see? We saw that Ex prime was equal to Ex, Ey primed is equal to gamma Ey minus VBZ, Ez primed is equal to gamma Ez plus VBY. So therefore, what is going to happen now? Here the magnetic field is 0, so the electric field simply becomes gamma eta by 2 pi epsilon naught y squared plus z squared 0 yz. Now you need to express this in the the primed coordinates. The primed coordinates, remember that only x and t will change. Y and z will remain untouched by a boost along the x-axis. So this essentially is gamma eta divided by 2 pi epsilon naught y prime squared plus z prime squared, and this is y prime and this is z prime. Okay, so this is the expression for the electric field, and this is very clear what has happened. So what has happened is, due to this velocity, the point is that the observer in the frame S prime, which is moving at a velocity v with respect to the frame S, the charge density in the wire, so the charge density due to Lorentz contractions, so in S prime, charge density due to Lorentz contractions becomes eta primed is equal to gamma eta, and hence there is this change in the electric field. Now what happens to the magnetic field? So the magnetic field, remember, was 0. So now let's see what happened to it. So Bx primed is going to be Bx, By primed is going to be gamma By plus V over C squared Ez. This is our transformations that we just found out. And Bz primed is going to be gamma Bz minus V over C squared Ey. So let's write down the magnetic vector. So this is gamma eta into V divided by 2 pi epsilon naught C squared to Y squared plus Z squared. And now the entries have changed a little bit. So this is going to be Z and this is going to be minus Y, right? So this should be clear from the fact that you have, so Bx, By, Bz are all 0. So Bx primed is 0, By primed is gamma V by C squared into Ez, Bz prime is gamma minus gamma V by C squared into Ey. We know what Ey and Ez are. We have plugged it in, and this is the expression for B primed. In the primed frame, these Y primes and Z primes are Y and Z. So this just becomes gamma eta V by 2 pi epsilon naught C squared Y prime squared plus Z prime squared into 0, Z primed and Y prime. There's a minus here. So this is the form, okay? Now since in S frame S prime the charge density moves, the observer actually sees a uniform I. Current is there. So in S primed, the charge density moves. So the observer sees a uniform I out there. So charge density moves. So observer sees a uniform current. So I primed is equal to minus gamma eta into V. So this means that B primed is mu naught I primed by 2 pi root over Y squared minus Z prime squared into, if you remember your cylindrical coordinates, then this is just phi prime. This, remember, is exactly the form that we found from Ampere's law. Okay, exactly. So this, let's put a box in here now. This is exactly the form that we found from Ampere's law. We found from Ampere's law. So we see again that magnetic force can be viewed as a relativistic effect. Right? And and we see that under Lorentz transformations, what has happened is so this we see is that seemingly you can get what you would have got from Ampere's law just by looking at Gauss's law and doing a Lorentz transformation. So it must be that Gauss's law is related to Ampere's law by this Lorentz transformation, and that is going to be what you will see briefly in the next few minutes. Actually, what I will do is I will pause here and take a short break, and you shall get the next one in the next lecture, because yeah, so that's something that I want to emphasize a little bit more. So we are breaking this up again into another lecture, but that should be fine. These will be two shorter lectures. So, okay, so let me just re-emphasize. So let me also write the last line down. So we see that under Lorentz transformation, Gauss law must be related to Ampere's law. And this will become clear in the next lecture when we make sure, write this in a clearly relativistic language. We will see what has happened. So let me just take you briefly through what we did in the class today. So we started off, revising what we had done in the previous class. We looked at the form of the electromagnetic field tensor, and which was given in terms of a mu's by this expression. And then when we wrote down f upper mu nu, we had this if in the matrix form it was made up of e's and b's in this language. And the very important thing that we said was that under Lorentz transformations, f mu nu becomes 2 lambdas multiplied by f rho sigma. So if you were to look at the transform, now we wanted to explicitly look at transformations where we have the explicit form of these lambdas. When we looked at rotation, and this is something left for you as homework for you to see at home, is that we just recovered that the electric fields and magnetic fields will be rotated amongst themselves. There will be no mixing of electric and magnetic fields. But when we then looked at boosts, so we looked at boosts along the x-axis, and we sort of carefully looked at this particular transformation law, and we tried to figure out what the transformation would be. So let me just briefly take you through that. So this was the transformation law. So remember that there are sums. Remember that so sigma and rho are summed over. Okay, so any repeated indices means a sum, so these things are summed over. For example, if you wanted to look at f01, so f01 prime was given by, so you had to put mu equal to 0 and nu equal to 1. And carefully going through the steps, what we found is that the two terms that we were left with were given by this line here. Rest of the terms were all equal to 0. And so that meant that Ex primed was equal to Ex. So that was an important, that was the first thing, and you should carefully go through the steps yourself as well. Similarly, we could look at f prime 0, 2, and that led us to the fact that there was a mixing between electric and magnetic fields when we looked at the EY component. Okay. Here again, you just need to be careful about the indices, which ones are 0 and which ones are non-zero. Once you get the hang of it, trying to do one or two of these, you will see that this is very simple. Okay, but make sure that you're not missing out on some terms in the sum. Okay, so at the end of the day, where the dust settled, the final result was that, you know, if you had as boost along the x-axis, then the Ex primed and Bx primed remained the same as Ex and Bx. The rest of them actually changed, and there was this mixing between the electric fields and the magnetic fields. So now what we did is we went on to figuring out what happens when we look at a boosted line charge. And as you know very well, the expression when we are looking at the electric field due to a line with uniform charge, the electric field is given just by this expression. E of r is proportional to 1 over r. And similarly, when we are looking at a current moving in a wire, so we find that the B is given is again proportional to 1 over r, and it's along the phi direction. Okay, now so you place this uniform line of uniform charge density along the x-axis, and in that case we just wrote it in Cartesian coordinates instead of r and so on. So the distance r was now given by r squared would be x squared plus y x squared. No x squared, y squared plus z squared, and this is because we have placed the wire along the along the x-axis. Excuse my constant mistakes on this, please. So the magnetic field here is 0 because it's not moving or anything. Now we go on to a frame S prime which moves along the x-axis with the speed v. So according to the transformations that we wrote down previously, the electric field E is now given by this expression here. And you see that there has been, so the only change is that there is a factor of, gamma, which has entered. And the change is because the charge density will change due to these Lorentz contractions, and eta prime is just gamma eta. So there's not much happening there. But what is interesting is that if you look at what the field, what the magnetic field is. Magnetic field to start off was 0, so all the B's were equal to 0 here in this expression. So this was equal to 0, this was equal to 0, as was this. And so B prime was just given by the E's, EZ's and EY's, okay? So once we wrote this down, the expression for the B's was let me. So the expression for the B's was just given by this. So what happens is that in frame S prime, the charge density moves and the observer sees a uniform current I prime, which was minus gamma eta V. And if you plug this in, what you just find is that V prime is exactly what we found from the Ampere's law. So what we see again is that the magnetic force can be viewed as a relativistic effect, and we see that under Lorentz transformations, Gauss's law can be related to Ampere's law. In the next lecture, which will again be a short one, we will explicitly show what exactly the form of the Maxwell's equations take, so the nice pretty form it takes, and we will review what we have done in this part of the course, and that will for sure be the last lecture on relativity and electromagnetism, and then we will move on to something else after that. Okay, so yeah, so see you in the next lecture again. Thank you.